In this chapter, we will be looking at a different number system than what we're used to. It's not different in that we need to use new symbols for new numbers or anything like that. However, they are numbers that can only be encountered in very specific circumstances. And since these circumstances will show up a few times in our study of algebra, we'll need to introduce them here. Let's recall our work with exponents, or more specifically, square roots. We learned that for a square root to exist, it must be a non-negative number. We can define it like this. This is set notation, and it's read like this: the square root of x such that x is an element in the set n, or the natural numbers. Why was this the case? Let's recall what a square root asked of us. If you were asked to find the square root of 4, you would say 2. In other words, you would say that 2 is the root of 4 because 2 times itself equals 4. It is at this point you may realize that we have a gap in our study. We never covered what happens when we have a negative number as our radicand. What makes this unique is that there is no negative number in existence when multiplied to itself stays negative. That is because two negative numbers being multiplied always produces a positive number. So it was easy to initially say that the square root of a negative number didn't exist. What if we just assume that another number system exists, but we don't know what's in it yet? Let's call it C for the complex number system, since we already know that's what we're going to be studying. From this point, we need to extend our definition of square roots to include all of OR. That is, the square root of x such that x is an OR, or is in the set of all real numbers. We now need to add some rules to this definition for when x is greater than or equal to 0 and when x is less than 0. When x is greater than or equal to 0, we'll follow the normal rules for simplifying square roots. Now we need to explore what happens when x is less than 0. So let's start by looking at a square root containing a negative number. Let's look at the square root of -4. We know that there exists no number multiplied by itself that equals -4. But we do know such a number exists for +4. First, let's break this integer into two factors, 4 and -1. We know the square root of 4 to be 2, so we can easily simplify this as 2 times the square root of -1. What we're going to do now is hold this radical number in a constant variable. It's not really a variable, but maybe it'll help you if you think of it as such. If we let the square root of -1 equal I, we can simplify our number as 2 times I. We now have a placeholder for our negative square root. We're going to call this number the imaginary unit. It will be defined as the square root of -1 equals I, or I squared equals -1. Going back to our definition of the square root, we can now add in our second part for when x is less than 0. When x is less than 0, factor out a -1 from the radicand and set it equal to I. For example, the square root of -b equals the square root of b times -1 equals I times the square root of b. Now we're ready to introduce the complex number. A complex number is a sum of a real number and an imaginary number. The standard form of a complex number is a plus bi, where a is the real part and bi is the imaginary part. Let's practice simplifying a couple complex numbers and put them into standard form. Number 1. 36 minus the square root of negative 36. Since we see a negative term in our square root, we know we are going to encounter a complex number. Therefore, we are going to factor out a negative 1 from the negative 36 and then continue to perform the square root on the 36 factor. So we will have 36 minus 6i. Number 2, the square root of 50 plus the square root of negative 50. Here we have two square roots, but only one contains a negative number. This is still a complex number. We can perform the first square root with ease, giving us 5 times the square root of 2. For the second term, we can factor out the negative 1 from the square root and perform the square root on the 50 just as we did with the first term, leaving us with 5i square root of 2. Complex numbers aren't inherently harder than what we've done in the past, such as factoring rational expressions. However, I left these as the last chapter in Prerequisites for Algebra simply because of how strange and left field they seem. We will have a few more very short videos concerning the operations on the complex numbers, and then we will begin our study of algebra. Before I end this video, I want to give an update about the last video I wanted to post. It was another exercise video like the last OpenStax video I did. While I did record the video, about halfway through, the audio stopped working. Since that was a very long video, approximately 5 hours of pre-edited material, I decided not to re-upload that video, and I apologize for that. I will see you soon with the next video.